Now coming to packing fraction. The packing fraction can be given as isotopic mass minus mass number by mass number into 10 power 4. Okay. See, in general, isotopic mass are the actual mass of a nuclide will be less than the expected mass. In general, it will be less. So, see, it is actually because during the formation of a nucleus, some amount of mass is lost in the form of energy. So the actual one will always be less when compared to the expected one or the theoretical one. So packing fraction is in general negative. Let us suppose case 1. Negative packing fraction refers to a stable nucleus. Whereas a positive packing fraction refers to unstable atomic nucleus. And finally, packing fraction is taken as a 0 for carbon. Okay, for carbon 612, it is taken as 0 as a standard or reference. Okay, these all are the factors that influence stability of the nucleus. Okay. Now it is artificial radioactive. This is different from natural radioactivity. In this type of radioactivity, generally the products formed exhibit radioactivity. We start with something which is non-radioactive. When that is bombarded with a particle, we get a product. But this product, because it possesses unstable nucleus, it emits some particles. So when the product nuclide emits particles or exhibits radioactivity, we call it daughter nuclide. So in general, the daughter nuclide exhibits radioactivity. Okay. Such a radioactivity is artificial. Let me give you an example. See, when aluminium 1327, this is anyway stable and occurs in nature as such. When bombarded with alpha particle, forms phosphorus 1530. Along with that, a neutron. But see, phosphorus 1531 is stable, whereas here we got phosphorus 1530, so is unstable and exhibits radioactivity. This, of course, is the daughter nuclei because it is exhibiting radioactivity. We have started with something which is stable, ended up with unstable atomic nucleus. Now, this exhibits radioactivity. That means it emits some particles. It emits a positron and gets converted into silicon 1430. A positron is emitted. Okay, so artificially we have prepared or we have made something which is unstable, starting with a stable one. So this is called artificial. Okay. Let us now go for different types of nuclear reactions. First of all, what are nuclear reactions? Reactions in which one nucleus is converted into another by interacting with other nuclei or by bombarding with particles. Like alpha, proton, neutron, deuteron, etc. Okay. One nucleus is converted into another. Okay. Now coming to the different types of nuclear reaction. The first one is NTR. Nuclear transmutation reaction. See, these are the reactions in which a target nuclide by bombarding with some particles, also known as projectiles, are converted into product nuclide along with a new particle called ejectile. Target nuclide, the one that is bombarded with a particle. Projectile, particle used to bombard a target nuclide. product nuclide is the one that is formed as a result of bombardment of projectile on the target nuclide. And in this process, a particle is generally emitted and it is called ejectile. Let us take an example. See, when nitrogen nuclide is bombarded with alpha particle, we get O817 and H11. This is how the proton was discovered by Rutherford. You got the isotope of oxygen. Now say this is the target nuclide. This is the projectile. This is a product nuclide. And this, of course, is the ejectile. This can be represented in shorthand form as, see, the target nuclide is written onto the left hand side of the bracket and the product nuclide is written onto the right hand side of the bracket with the symbols of, remember, the symbols of projectile and ejectile written within the brackets. Okay. Symbols are used for projectile and ejectile. Okay. This is about the nuclear transmutation reaction. Now it's nuclear fission. The nuclear fission is a type of nuclear reaction in which a heavier nucleus is broken down into two nuclei of intermediate masses. Along with the release of large amount of energy. On bombarding with thermal neutrons, nothing but slow speed neutron, thermal neutron or slow speed neutron. In this, a heavier nucleus is broken down, undergoes a fission into two nuclei. We can say two lighter nuclei of intermediate mass. Along with that, enormous amount of energy is released. Let me give you an example. See, when a uranium nucleus is bombarded with thermal neutrons, slow speed neutrons. We get two lighter nuclei of intermediate mass, barium and krypton. With the release of large amount of energy, about 200 million electron volts. Now see, this is thermal neutron, and the neutrons that are formed are called secondary neutrons. You know, in general, we get 3 neutrons or 2 neutrons, or even sometimes 4 neutrons also in very few cases. So on an average, 2.5 neutrons are formed per fission. These are called secondary neutrons, and you know, these secondary neutrons are responsible for chain reaction. Let me give you some more examples with different number of neutrons. You may get xenon and strontium. Plus, say, energy. Now, when the same thing splits up to give rubidium and cesium, we get 4 neutrons. That's special. Look at this. 3 neutrons or 2 neutrons or 4 neutrons in very few. Okay. Let us see the characteristics of this. You know, uranium 233, uranium 235, and even plutonium 239 undergo fission with the thermal or flow speed neutrons. Okay. Whereas thorium 9232, uranium 238, protactinium 231, 91, 231, and neptunium 237 generally undergo fission with fast neutrons. Okay. Coming to the chain reaction. Let us see what happens. See, when a neutron is captured by a uranium nucleus, it splits into two nuclei of intermediate masses. Let us say the same barium and krypton. At the same time, we get 3 neutrons. Of course, some amount of energy. Now, these 3 neutrons are called secondary neutrons, and they are again captured by 3 uranium nuclei, on which again we get nine neutrons plus, of course, 3 energy. I mean, every time 3 neutrons and 1 energy. This is how then these 3 into 3, I mean 9 neutrons, they are again captured by uranium nuclei. Okay. And again, you get neutrons along with the release of large amount of energy. In this way, the number of neutrons increases in geometric progression. Right. And that at one stage leads to explosion. Now, if you want, you can give a relation. At a particular stage, number of neutrons and of course energy can be given as 3 power n. Suppose in the first stage you got 3 neutrons. In the second stage you got 3 square, I mean 9 neutrons. Energy can be given as 3 power n minus 1. In the first stage it is 3 power 1 minus 1, that is 3 power 0, nothing but 1. The same way at the second stage, 3 power 2 minus 1, you got 3 energy. So this is about chain reaction. This, of course, is the principle involved in atom bomb. This chain reaction can, of course, be controlled for peaceful purposes, like for the production of electricity. Okay. Let's see. Using a nuclear reactor, a chain reaction can be controlled. Okay. Then what are the important things used in a nuclear reactor? The first one is fuel. Fuel may be of two types. Fissile and fertile. Fissile. These are used directly in fission reactions. That means they directly enter into fission reaction and result in a chain reaction. Okay. For example, we have uranium 235, plutonium 239, even uranium 233. These generally undergo fission by slow neutrons. Okay. I mean thermal neutrons. Now the second variety, fertile. See, these are the fuels which are non-fissile. They cannot directly enter into the reaction, but can be converted into fissionable material by the action of neutrons or by bombarding with the neutrons. As such, non-fissile, but can be converted into fissile material by bombarding with the neutrons. Okay. For example, remaining those which undergo fission with fast neutrons. Uranium 238, thorium 232. Okay. Next. Undergo fission with fast neutrons. This is interesting. Direct, indirect. Undergo fission with thermal neutrons. These undergo fission with fast neutrons. This is how the fuel is of two types. Coming to control rods. See, control rods are used to absorb some neutrons, not all. Because by absorbing some neutrons, you can control the chain reaction. See, for this purpose, we use boron or cadmium rods are used as control rods. Okay. Then there is moderator. See, moderator is used to reduce the velocity of neutrons. I mean to slow down the neutrons. For example, heavy water, graphite, these are used as moderators. Now the last one, coolant. See, this coolant is the one that converts the energy produced during the fission reaction into heat energy. That, of course, is cooled down. Material that transforms energy produced during fission reaction into heat energy. Okay. For example, we have some alloys along with heavy water. We can use this alloy, and of course some polyphenols are also used. These are the materials used in a nuclear reactor to control the chain reaction and to utilize the energy that is released for the production of electricity.